Howdy. In this video, we'll be talking about the general transfer functions for the four common filters. We will be discussing the transfer functions for both the first and second order high-pass and low-pass filters, and we will discuss the transfer functions for second order band and notch filters. So whenever you're given a circuit and you're trying to solve for its transfer function to determine what kind of filter it is, your transfer function may not look exactly like what these general transfer functions look like. That just means that you need to manipulate your equation to get it into one of the forms shown. So here we have an example of a first order low pass filter. You have A naught over S plus omega naught. A naught is the gain of the filter. Let's say you have a passive filter, that gain will be 1, so A naught will be 1. And omega naught, like I said, is the cutoff frequency of the filter. So let's say you take the limit of this transfer function as omega approaches 0. So when you do that, you will get A naught over omega naught, which will be some constant value. And then let's say you take the limit of this transfer function as omega approaches infinity. When you do that, you'll get 0. So graphically what this looks like, we have frequency over here on the bottom, and then we have the magnitude of our phase on the y. So to start off at some constant value A naught over omega naught, and then it'll decrease to 0, just like so. So as an example of this, we have this transfer function. We have 1 over S plus 2. We have a gain of 1 and then a cutoff frequency of 2. So you can see here that it starts off at some constant value here, and it decreases as the frequency increases. So at frequencies below our cutoff frequency is about right here. Frequencies below our cutoff frequency, in this region, the signal is allowed to pass through. Above it, the signal is not allowed to pass through in this area here. So what that means is low frequencies are allowed to pass, high frequencies are not. Therefore, it's called a low pass filter. Another low pass filter is a second order low pass filter. Here we have H naught, which is the gain, and omega naught is still the cutoff frequency. So again, if you take the limit of this as omega approaches 0, you'll get a constant value. If you take the limit as omega approaches infinity, you will get 0. So it'll have the same basic shape as our first order low pass. The only difference is, well, and also depending on your coefficients, will have different cutoff frequencies and gains, but the same general shape, and the roll-off will be steeper.
So this is the general transfer function for a first order high pass filter. So again, you need to manipulate the transfer function that you have gotten from your circuit into this form so that you can figure out the coefficients. So the transfer function is A1S over S plus omega naught. And so A1 is the gain of the filter, and for a passive filter, A1 would equal 1. And omega naught is the cutoff frequency again. And so if you take the limit of this transfer function as omega approaches 0, your transfer function will equal 0. And the limit of your transfer function as omega approaches infinity is a 1. And so the way this looks graphically with omega on your x-axis and the magnitude of your transfer function on your y-axis is that it starts off at 0 and then it eventually goes to a 1. And this is what the general shape of a high pass filter. So this is an example of a high pass filter where your cutoff frequency is set to 2 and your A1 is set to 1. So this is a passive filter. And you can see how all the frequencies above 2 is allowed to pass, and all the frequencies below 2 are attenuated, which is what a high pass filter does. And so this is the general second order transfer function for a high-pass filter. In this function, H naught is set as the gain of the filter, and omega naught is the cutoff frequency again. And when the limit of this function as omega approaches 0 is 0, and the limit of this function as omega approaches infinity is H naught. And
so here we have a second order bandpass filter. We have H naught, which will be your gain, and then we have omega naught, which again is the cutoff frequency. Q is selectivity of filter. It also determines the bandwidth of your filter. So again, if you have a passive filter, H naught, the gain will be 1, indicating no gain. So if you take the limit of this transfer function as omega approaches 0, you will get 0. And then if you take the limit of this transfer function as omega approaches infinity, you will also get 0. It's a little confusing, but when you look at it graphically, it's shown like this. So as our frequencies, as we said, when we take the limit of the transfer function as omega approaches 0, so going this way, our transfer function will approach 0, which is what's shown here. Same thing as our frequencies approach infinity. It goes towards 0. So what that means is that at the extreme frequencies, extreme high, extreme low, the signal is attenuated. And at signals around our cutoff frequency, this area, they are allowed to pass. So we have a band of frequencies where the signal is allowed to pass. That's why it's called a band pass. This example, we have H naught is set to 1, so we have a gain of 1, and then omega naught is set to 2, so our cutoff frequency is 2.
so this is the general transfer function for a second order notch filter. And this function, H naught, is the gain of the filter, and for a passive filter, it would be set to 1, and omega naught is the cutoff frequency of this filter. So if in this case, we are going to take omega z is equal to omega naught. And so if you take the limit of this transfer function as omega approaches 0, you get H naught. And if you take the limit of this transfer function as omega approaches infinity, you get H naught. So in order to see this better, this is an example of a general transfer function for a second order notch filter where your gain is set to 1 and your cutoff frequency is set to 2. So you can see from this Bode plot how almost all the frequencies are allowed to pass except for the frequencies that are close to the cutoff frequency. These are the only frequencies that are attenuated, so it creates a notch basically in your graph, and which is why it is called a notch filter.